Hello everyone, my name is Niel. Today I'm very glad to present geospatial situation detection through FlinkCEP. Before the presentation, a little bit about myself. I have been working at Uber for about 3 years now, and previously I worked on dynamic pricing. Now I work in Uber AI as a software engineer, focusing on applied machine learning. This is the outline of the talk today. First, I would like to describe what is a marketplace. What does a marketplace do inside Uber? Then we'll switch to probably one of the biggest challenges within a marketplace, observability problem. I'll go through the technical details of how we build large-scale clustering algorithm with Apache Flink, and how we use complex event processing to detect mine information from those complicated geospatial patterns and sequences. Lastly, I would like to talk about some tips and tricks, lessons learned from our experience building Flink application. What is marketplace? Marketplace is like the brain behind Uber. Every time we order a car, we're trying to get a food delivery, there's a whole bunch of work being done behind the scene. A lot of them is the marketplace. Remember, Uber is operating this physical world with a physical global logistic network. We have to make millions, if not billions, of micro decisions all the time. And those decision makings are powered by this real-time engine within marketplace. Part of the marketplace is trying to predicting and forecasting the future of the world, the future state of the marketplace, of the market, so that we can make a plan in advance. Another part of the marketplace is trying to run real-time optimization. Based on the information we have, we want to make decisions that are optimized so that we can support the Uber marketplace, the Uber service, running all the time as smooth as possible and as efficient as possible. Marketplace consists of multiple teams. We have forecasting team, who's responsible to predicting and forecasting the state of the world using various cutting-edge machine learning methods. We have dynamic pricing team, whose dynamic pricing platform computes the search multiplier for every trip, for every request. Every time you open your app, the search multiplier is computed by that platform in real time. The matching between riders and drivers, couriers and eaters is powered by intelligent dispatch platform. We also have driver rider pricing, marketplace health, marketplace platform, which builds the infrastructure that supports all of the functionality above, and provide real-time high-fidelity data and metrics to surface real-time dashboard. Let's talk about our problem, observability problem. Think about if you live in a city that there's a concert where a football game is about to over. You are trying to get home by taking a car. Obviously, it may cause some problem to local traffic. You are trying to get home at approximately the same time, approximately the same location. It may cause traffic jam. It may increase the wait time, and it may impact your Uber experience. So how do we detect these scenarios in all of our markets? How do we detect these scenarios as early as possible and address it as early as possible? Previously, this was done by people on the ground who is very familiar with the city, familiar with all the events, holidays happening in the city, and can take a close look at it. Take a close look at it 24 hours. Obviously, this is not scalable. How do we scale observability? Uber is operating in 700 plus cities around the world across multiple time zones. The sheer scale of these problems makes it even harder. But second, every market is different. Every neighborhood, every block, every corner is different. Cities are under different regulations. Cities have different road network, different traffic pattern. Also, Uber's problem is essentially a space-time high dimensionality problem. All of the decisions, models we run are under this high dimensionality assumptions. We also have to do this in real time, so there's also a latency constraint on it. Sounds like a problem that's impossible to solve. Imagine we have 8 devices across the world and distributed unevenly on the ground. Each device communicates to us with their GPS location associated with it, so that we know where they are. But the sheer amount of data flooding in is enormous. It can overrun any system with any person who's trying to extract meaningful information from it, simply because we have a limited bandwidth. So it is important to have a dynamic zooming functionality, act like a filter out the irrelevant information, only keep the relevant ones. It's a dynamic zooming feature that can only look at those important areas and hotspots and ignore the noise. This is basically a geospatial component of the problem. Secondly, remember that we're operating this space-time high-dimensional space. Not only we want to look at the static snapshot of the world, we want to look at how things evolve, how those scenarios evolve over time. It could last for 2 minutes, it could last for about an hour with days. So on the temporal dimension, we use computer event processing to do pattern matching of those sequences produced by the previous steps, which I will talk in details later. Lastly, all of the result is being served to our end user through real-time dashboard, email alerts, or other alerting systems. This talk is basically how we use Flink and the FlinkCEP library to implement the dynamic zooming features and how to do pattern matching on temporal sequence. First, we need to define what is a region. The image here shows that around the city, in the city, you can see there are many hotspots. We only care about those hotspots, and we want to monitor the health and the status of those hotspots and ignore the others. So the region definition here is basically a geospace that shows that's generated by the clustering maybe of the same type of events or exhibit some similar business characteristics, business metrics. Also, one single region has to be a connected geospace. It could be an arbitrary shape, a square, circle, or any shape actually. And since we have to do this around the world, it must be cheap in computation. Naturally, we turn to clustering algorithm to help us. We really look at 2 families of clustering algorithm. The first one is called k-means, which is widely used and known for cheap computation. But it also requires the user to predefine the number of clusters, the number of centroids you want to find. And k-mean only works well when the clusters are equally shaped, which is not the case in our problem. So we turn to density-based clustering algorithm. Density-based clustering is flexible in terms of it doesn't require a fixed number of clusters, and the cluster be arbitrary shape. It's also relatively cheap in a small data set, but we have to test it on our problem, on our scale. So we choose the simplest version of density-based clustering, which is called dbScan, density-based spatial clustering with noise. It's pretty straightforward. Think about you have points of the world on the map, and the clustering procedure begins with you randomly select one of the points, and you draw a ball with a certain radius. That radius is called ipsilon. It is a parameter of the algorithm. Then you define the threshold. If the number of points within the ball is above the threshold, you identify the center point as the origin of a cluster. And then you apply the same procedure on its neighbors and in iterations and expand the cluster. The procedure ends when you go through all of the points on the map. So it's straightforward, easy to implement. However, even with auxiliary data structure, the complexity is too much. We can use TD tree or data structure optimized for spatial search, but it's still not good enough for our scale. It's not very efficient on streaming data. In the worst scenario, the really naive approach caused n-squared complexity. So how can we do better? The reason why dbScan is expensive because we have to do this pairwise computation between potentially all pairs of points. So the problem is the space is huge. One simple approach is to discretize the world into several buckets. By using buckets, we can transform the complexity of the problem from the number of from the geospace to the number of distinct buckets. Also, we can tune the resolution of the bucket as well. Here we use H3 library, which is developed by Uber a couple of years ago. H3 library allows us to divide the world into hexagon grid, hexagon cells. Here, I would like to briefly, probably oversimplify the way that H3 do geoindexing. First, we have Earth, and then we create a icosahedron, a project that on the Earth surface. For each triangle tile, we divide that triangle into 7 hexagons. And for each hexagon, we can divide into 7 more subhexagons. We can apply this procedure recursively until we get desired resolution. There are several options open source. People usually use GeoHash, and there are also S2 library developed by Google. And the reason why we use Hexagon is because Hexagon has this nice properties called the uniform agencies, which means that Hexagon only has single kind of neighbor in all directions. Squares, triangles have different kinds of neighbors. The disadvantage of Hexagon makes it perfect for modeling flows and distance-based applications. Also, the Hexagon provides the lowest space distortion, which is essential if you want to do machine learning on GeoBucket data. How do we implement dbScan in hexagons? So instead of identify origin of a cluster within the ball, now we move to the hexagon world. We first tune the hexagon to fit to the size of the ball. Then we see the number of points inside the hexagon. If the number of points is above the threshold, then we identify the hexagon as a core hexagon. A core hexagon is basically the origin hexagon of a cluster, and all of the neighboring hexagons belong to the same cluster. After we identify the core hexagon, we apply the same procedure to other neighbors to propagate the cluster. And until we go through all of the hexagons that have points in it, it's greatly reduced our compute complexity. Another nice property provided by H3 library is that it offers multiple resolutions, ranging from the hexagon covering the whole continent down to a single hexagon cell is about 10 square foot. Also, hexagon has this nice property. H3 has this nice property that hexagon naturally has hierarchy relationship, which makes it easier for compression in data transformation and or storage. Now we have the geoindexing library. We know the algorithm. How do we implement streaming? We researched multiple papers. We found this one very informative, which is called DG to CEP, a near real-time online algorithm for detecting spatial cluster large data streams through complex stream processing. This is a paper published in 2019. I highly recommend reading it if you're interested in streaming clustering. Our work is also inspired by this paper. There are 2 ways of implementing clustering on real-time data. The traditional way is to use batch. Basically, for each time interval, periodically we batch all the points all the events into a single window. Then we run the clustering algorithm on it and produce the whole cluster as a result. We choose a different one. We implement the clustering algorithm in a full streaming fashion, which means that there's no window or accumulation stage. The data is always moving. How we do it? Basically, for each event comes in, our cluster operator see if that event creates a new core hexagon or destroy a core hexagon. Basically, does it make any delta to our clusters? If it does, instead of passing the whole clusters as a result, we only pass the deltas as changelog to the downstream consumers, services, operators. So assume perfect orders. The downstream consumers can take the changelog and reproduce our clustering results in perfect consistent with the cluster operator. This is also nice because we smooth out the spiky workload because we distribute the work across time. The workload becomes more smooth. Also, we publish a changelog to our logging pipeline. For offline analysis, we can use the changelog to fully recover the clusters. By combining our approach with the event time semantics offered by Flink, we can implement our back testing and produce the same result as our online search system. This is also very, very important in our problem because we want to implement observability system for alerting and want to tune and calibrate alerts rules based on what we see. Clustering on streaming data. For changelogs, there are really two categories of changelogs. The first one is addition, second is subtraction. For addition changelog, we create we have three subtypes. For each event comes in, does it create a new core hexagons? Does it update existing core hexagons? If it does, we update the hexagons and notify all the nearby neighbors. We also probe the neighbors to see if they already have clusters exist. If there is, we have to do this merge operation. Merge the new cluster with old cluster into one. This could be expensive because potentially it has to go through all the hexagons exist. But in reality, it's pretty rare. And when the user event sequence stopped, we create a disperse event. And the cluster operator take that event to see that if it does have subtraction impact on our clusters. If it does, we again destroy the cluster, notify the neighbors, and see if the rest of the hexagons produce different clusters. If they do, we apply the split operation. It's also expensive for the same reason I discussed in the previous slide, potentially go through all of the hexagons on the map. So we have the streaming clustering platform. However, the started clusters are still not good enough because as I described in the beginning of the presentation, we have the geospatial component, we also have the temporal component. So we want to see the evolving scenarios along the time, not just like a static snapshot. Also, if we treat each cluster independently, the sheer number of clusters is just overwhelming. It's too big to be useful. How we identify this evolving situation, this evolving patterns within those clusters. This is where complex event processing comes in. We first introduce a concept called situation. Situation is really a clusters in motion. It's a set of clusters. This example shows that we have 3 clusters generated at consecutive timestamps. So because they share a large overlapping area, we merge them into one situation. So a situation is really just a sequence of consecutive clusters. We merge them, associate them together because they share some similar characteristics. This really reduces the number of entities we want to look at. To implement this, we use complex events processing library. So for those who's not familiar with it, I can give a very brief introduction to it. What does it do? So FlinkCEP is a library built on top of Flink runtime. What it does is, compared to a very simple filter operator, a CEP detects patterns and filter events based on patterns in sequences. The user must define the input stream, also the pattern the user wants to look at. Then the compiler, during compile time, the pattern is being compiled to a non-finite automata. This is all done by FlinkCEP out of the box. In the runtime, when event comes in, first they're stored in a buffer and ordered by event type. Remember that the order really matters in complex event processing because different orders produce completely different results. After the event comes into the automata, we track the state and state transition and see if it reaches the terminal state. Our use case is special compared to the traditional CEP applications because we use cluster as a primitive event. The reason we use it is because we want to build situation on top of this cluster primitive. Here, a simple example is to use CEP to detect and merge overlapping clusters into one. On this picture, different colors indicate the cluster is generated by different type of events. And the x-axis is the time dimension. You can see we merge the red clusters into one situation. We basically associate them together and detect that the situation is expanding to larger and larger area. And the green ones are shrinking into small area and eventually will disappear. By doing this, we can track the duration of the situation. Our cluster abstraction works really well with the CEP library. Even more, we can detect even more complicated patterns, not just clusters with scenarios on the same location, but scenario situations across long distance and across long time horizons. For example, some situation happen in the morning in downtown area may correlate or cause some situation happen in the suburb in the afternoon. We want to see those correlations, and this is easy to implement by apply complex event processing on situation events. Here is a very simple example that we want to see if the green situations, if the red situation is always followed by the green situation. If it does, we produce another complex event and notify the end user. To put everything together, we have the clustering algorithm, the geo-indexing, and we have the situation part that do the temporal sequence matching and merging. However, the end result is being served as real-time dashboard to our end users, and we expect end users to combine the human expertise and domain knowledge to recalibrate and adjust the model that will identify those situations, so that the pipeline, the system can produce results more accurate over time. This is very important. This through a negative feedback loop ensure that the human expertise and our CEP pipeline can be combined together to produce valid results. When the user decides to adjust the rule or adjust the model accordingly, you have to do this on real time without restart of the whole clusters. To do this, we leverage Uber infrastructure, specifically the dynamic configuration infrastructure. For each task manager, we have a daemon process, the agent process that keeps listening for changes. If there is a change happen, the agent communicates to the task manager through the local file system. All the tasks can pick up the complete change in runtime without restarting the job. Lastly, I want to talk about some tips, tricks, and lessons we learned from our journey using Flink. First one is the staggering window. This was also talked about by a presenter, I believe, in the previous Flink 4 conference. So what the staggering window means, it basically address the problem that the Flink window assigner always assigns the same in time for all panes across multiple partitions. No matter how many partitions, how many parallelisms you have, all the windows always end at the same time. All the panes always end at the same time. So it causes problem what is called thundering herd problem. It means that all the compute load and I/O load all peak at the same time. It creates the low utilization of the resource because they're idling for the rest of time. Also, if your pipeline has internal events generated in a flat map fan-out fashion, this will also amplify the problem by multiple large magnitude. So the solution is a simple modification of the Flink window assigner. In our solution, for each partition, when the window assigner is trying to assign a pane, we introduce a random offset. By doing this, different partitions have different end time. Different windows in different partitions have different end times. But also, we need to make sure within the same partition, the offset is consistent, so the result is correct. The result is pretty straightforward, as we can see on this graph, that the peak workload greatly reduces because we simply just offset the windows, offset panes, and redistribute the workload across time. The workload becomes more smoother. Also, the throughput becomes more smooth. I want to emphasize it does not only have benefits on the Flink pipeline, it also benefits downstream services. We find that by introducing this change, the downstream service and database, their GC time decreases, the latency of read and write requests also decreases. This image shows a before and after of this change. Lastly, I want to talk about our experience using machine learning on streaming data. Machine learning is a hot topic, but apply on streaming data is quite different from traditionally the batch training on static data. Usually in Uber, we have models to predict estimated quantities in our marketplace. Usually those models are trained with offline historical data in a periodic fashion. However, as we all know, traffic patterns are demonstrate obvious trends, and many of our data inputs have the nature of non-stationarity. So our offline models does not perform well on those data. So our solution is combine the offline models trained with historic data as a baseline. Then we stack an online calibration module on top of it that take the deviation from our prediction and the real-time signal, use that to readjust our offline model. This is easy to implement, to maintain, and it works fairly well. But our experience is that there's a tricky balance in this approach. First of all, we want to model the non-stationarity of the data. We want to fit to the real-time signal, but we also don't want to overfit to the noise. So we want to emphasize here is that there's some nuances, there's some tricks that in balancing this ability to fit, to adjust to real time, whether it's signal or noise. And I believe my presentation ends here. And for anyone who's interested in talking about machine learning on streaming or geoanalytic streaming applications, feel free to send me an email or connect on LinkedIn. Thank you so much.